Good evening, class. Welcome back to Living Systems 1. We are now in week 7 of semester. It goes very quickly, doesn't it? And tonight we're going to visit the concept of acids and bases. Very, very important area. For all students regardless of your major. We're going to look at some of the properties of acids and bases. What does it actually mean to be an acid or a base? And hopefully from that discussion, we'll have a better understanding of what the pH scale is all about. So this is our second last lecture in the chemistry component of living systems, even though a lot of the chemistry does flow into the biology component as well. So it's always a good place to start. All right, so let's start with a definition. And the earliest definition was given by this Swedish chemist called Arrhenius in the 19th century. And Arrhenius proposed that an acid contains a hydrogen atom and it dissolves in water to form a hydrogen ion, H+. And before we go any further, let's just recap something. And I'll just get my pen here. So of course, you know from the periodic table, hydrogen has the number 1 here and the number 1 below it. And that tells us that it has 1 proton and it has 1 electron and 0 neutrons. So imagine that a hydrogen atom lost its electron, so that now that proton doesn't have a balancing electron. That would give us the ion. And of course, the hydrogen ion is just a proton. That's all it is. It's referred to as a naked proton. And for that reason, people often refer to the hydrogen ion as just a proton. They call it a proton. So you'll hear me using this term, proton, quite often in this lecture. And when I do, you know I'm referring to the hydrogen ion. All right, so let's go back to our definitions. An acid contains a hydrogen atom and dissolves in water to form a hydrogen ion, otherwise known as a proton. And here's an example. So we've got an acid here. This is hydrogen chloride. This is the gaseous form of hydrochloric acid. So when I see that, I always want to say hydrochloric acid. In this case, we say hydrogen chloride. Dissolves in water, and when it does, it dissociates. That is, the hydrogen ion, the proton, separates from the chloride component. In other words, the two ions that originally came together to form HCl in the first place. All right, Arrhenius also proposed that a base contains hydroxide. That is OH. Base contains hydroxide, and when you dissolve that in water, it will form the hydroxide anion. So let me just clear all that. So here's an example. Here's a very commonly used base, sodium hydroxide is the name. And when we dissolve sodium hydroxide in water, once again, you get this dissociation taking place. That is, they split apart from each other to form the sodium cation and the hydroxide anion. So really good to remember, hydroxide is very important in acid-base chemistry, and of course, the proton. Now, these definitions are really good. They're really good definitions, especially considering the fact that Arrhenius proposed these in the 19th century. Always amazes me how clever these people were, given that they didn't have the technology that we have today, they didn't have the equipment, and so on. So really good definitions, but the Arrhenius definition is not always very inclusive. That is, sometimes it doesn't cover, the Arrhenius definitions don't cover all the cases of acids and bases, all the examples. All right, so one problem with the Arrhenius definitions is that the naked hydrogen ion, that is the proton, doesn't exist, or rather doesn't exist for very long in water. It is a very reactive and very transient species. And instead it tends to react with molecules of water, or rather with a molecule of water, to form what's called the hydronium ion. And this is an important one for you to remember, H3O+. This is the hydronium ion. So this is what happens when water picks up a proton. And we can look at that here. So here's our proton here. And that can react, it can react with a molecule of water to form the hydronium ion. So let's look at what's happened there. So rather than H2, which we have in a molecule of water, after picking up this proton, the H2 becomes H3. Take note of that positive charge. Where did that come from? It came from the fact that the water molecule has picked up a positively charged proton, but without that balancing negatively charged electron, and hence why the single positive charge on the hydronium ion. All right, in the 20th century, Bronsted and Thomas Lowry came up with a new definition, and this is the definition that's still used today. And they proposed that an acid, a Bronsted-Lowry acid, is a proton donor, and a Bronsted-Lowry base, or let's just say a base, is a proton acceptor. So really simple, but really, really useful definitions. An acid donates a proton, a base receives a proton. And we can see that here in this reaction. So once again, we've got hydrogen chloride, and in this case, this particular species is going to donate this proton, not the entire hydrogen atom, but just the proton component. In other words, it's going to leave its single electron behind. So because it's donating a proton, this makes HCl an acid. In this particular reaction, water is going to receive that proton. Because it's receiving that proton, we can classify water in this particular example as a base, because it's accepting that proton from the acid. So what's formed as a result? Okay, so the HCl gives up its proton, and what does it end up becoming? Here's the product. It becomes the chloride anion. And remember, it's picked up that negative charge because it now has the electron, that one electron that originally belonged to the hydrogen ion. Okay. So that's chloride. Now, what's happened to the water? The water is accepting that proton from the HCl. So the H2O becomes H3O, which is our hydronium ion. And remember where that positive charge has come from, because the water molecule gained a proton, just a H+, which means there's no balancing electron that's come with it. And this confers a positive charge to this hydronium ion. All right, so HCl is termed an acid because it donates a proton to the water. And water is acting in this case as a base because it accepts a proton from HCl. All right, can everyone still hear me? I'm worried now that my audio will drop out again. Can someone confirm? Excellent, Excellent. All right, so an acid must contain a hydrogen atom. And that doesn't mean that all compounds that contain hydrogen atoms are acids, because an acid needs to be able to donate the proton. Okay, so let's look at some common Bronsted-Lowry acids. But before we do, here's an abbreviation used for a general acid. And it's simply a H, which refers to the proton that can be donated, and then A refers to the rest of the acid molecule. So HA, just a sort of a general convention used for acids. All right, so let's look at some common acids here. You're probably all familiar with hydrochloric acid, HCl, and in red is the proton, of course, that will be donated, and there's only one proton in this example, or rather one hydrogen in this example, and we refer to this as the acidic proton, the one that will be donated. Here's another one, hydrobromic acid, probably not so common, HBr. Nitric acid is definitely more common, HNO3. Sulfuric acid, very commonly used, H2SO4. And here's an interesting one, which everyone will be familiar with, acetic acid. So where would you commonly find acetic acid? Can someone tell me? Acetic acid, and in this case we can see all the bond lines, all the covalent bonds. Where would we find acetic acid? Any idea? Soft drink. Acetic acid in soft drink. Well, I'm not sure about that. In my wine. Someone said in my wine. Oh, that's not very good. Protein. I'm not sure about protein. But yes, in wine. So for you winemakers, acetic acid is not your friend, because when ethanol oxidizes in air, it can form acetic acid, and that's going to make your wine taste very bad. It'll make it taste sour. So definitely not the winemaker's friend. But where you would most commonly find acetic acid is in vinegar. It's the main component of vinegar. And of course, we don't want to taste acetic acid in wine. But anyway, so this is one molecule of acetic acid that you can see here. We've got 2 carbons. This carbon, of course, is bonded to 3 hydrogens. This carbon has a double covalent bond to an oxygen, another covalent bond here to oxygen, which in turn is bonded to this hydrogen. Now, this is the hydrogen, or rather the proton component of that hydrogen, which is donated, which is lost. So this is the acidic hydrogen here, not these ones. These ones tend to be held onto quite tightly, but this is the one that's actually donated by acetic acid. Okay, so there you go. I like that answer, in my wine. Very good. All right, let's move on. Okay, so we've seen hydrochloric acid with 1 acidic proton, and so this type of acid is called a monoprotic acid. Sulfuric acid has 2 acidic protons, so it's called a diprotic acid. And then we've got something like phosphoric acid with 3 acidic protons, and it's termed a triprotic acid. So even though any acid has an absolute requirement to contain 1 or more acidic protons, the acid itself may be a neutral molecule, as you can see here, or it can carry a net positive charge or a net negative charge. All right, let's move on now to bases. So, as we saw earlier, a Bronsted-Lowry base is a proton acceptor. So because it accepts a proton, that means it must be able to form a bond to a proton. In order to be able to form a bond to a proton, which of course doesn't bring any electrons to the party, the base needs to have a lone pair of electrons, a non-bonded pair of electrons, where those two electrons can form that covalent bond to that incoming proton. Okay, so a base must contain a lone pair of electrons that can be used to form a new bond to the proton. And this is a classic example that we can see here. So you've been introduced to this particular compound here, NH3. This is ammonia. And you might remember from earlier lectures that nitrogen has 5 valence electrons. It wants how many? It wants to be surrounded by how many valence electrons? 8, correct. It wants that octet. Okay, so in order to achieve that, it uses 3 of its valence electrons. Hold on, I'll just get my pen. It uses 3 of its valence electrons. 1, 2, 3. It uses 3 of 5 to form covalent bonds with 3 hydrogens, and in doing so, of course, it's now surrounded by an octet of electrons. All right, but what's really important, that was just a bit of a revision there. What's important is that it has this lone pair of non-bonded electrons. And that's important because it means that ammonia can actually act as a base. That is, it can accept a proton, and in this particular reaction of ammonia with water, it can accept a proton from a molecule of water to form NH4+. What is this called? NH4. What's the name of this species? Oh, my drawing gets worse every year. What's this called? Who remembers what this ion is called? Ammonium. Wonderful. This is the ammonium ion. Correct. So hopefully you can see that in receiving a proton, so remember this is the incoming proton, yep, which is just H+. Okay, it's not bringing its own electron to the party, but the 2 electrons that form this covalent bond were originally this lone pair of electrons here. So because what was originally ammonia has picked up a proton with no balancing, without a balancing electron, it means that the ammonium ion has picked up this single positive charge. Okay, and of course then we look at water. So in this particular instance, water is acting as the acid because water is donating one of its protons. It's losing one of its protons. And as a result of water, the water molecule losing a proton, it becomes the hydroxide ion. Okay, it loses a proton, but that what was originally the hydrogen atom has left its electron behind on the OH, and hence the single negative charge. Okay, so hopefully that makes sense. All right, give me some feedback. Does that make sense? That's always a little bit tricky for students to understand, especially at this time of the evening. Okay, we've got 1 yes. All right, so common bases. But before we look at common bases, here's this abbreviation for a general base. Is there another, we've got a question, is there another example in the textbook? Yes, you will find several examples, several different examples in the textbook. Absolutely. All right, so here we have B, obviously for the base molecule, but also we have these 2 dots here that represent the lone pair of electrons that's required to receive a proton. All right, so bases can be neutral molecules such as ammonia or water, but more commonly bases are anions, and this would be the number one, the hydroxide anion. This is the base, or this particular base is derived usually from a metal salt. So here's an example of a metal salt, sodium hydroxide, and of course it's a metal salt because the sodium, as per your periodic table of the elements, is classified as a metal. And the same thing applies to potassium hydroxide, magnesium hydroxide, and calcium hydroxide. So let's look at the concept of proton transfer a little bit more closely. All right, so here's our general acid. So remember, this is the acid molecule, this A, and this is the proton that will be transferred. Here's our general base with the lone pair of electrons that can form a bond to a proton. All right, so when this proton is lost from the acid molecule, we can see here that it's being lost, then this electron pair that's forming that covalent bond, as I was just saying, that actually stays behind, that stays with the acid molecule. So as I was saying, the electron that's normally associated with the hydrogen atom, it actually stays behind. So only the proton itself, the proton component of the hydrogen atom, is actually lost. All right, so when that happens, what does the resulting product look like? So this is what we started with, HA. What happens to it? It now looks like this after it's lost its proton. It's A without the H, but it has now a lone pair of electrons. So where did that lone pair of electrons come from? It came from this original bond here. And of course now, because the acid has the electron from the original hydrogen atom, it picks up a single negative charge because that electron that stays behind no longer has its balancing proton. All right, so let's look at the base. So the base starts off, of course, with a lone pair of electrons, which can form a covalent bond to the incoming proton that came from here. All right, so it gains a proton. That proton can form a bond because of these electrons, a covalent bond. And then the base ends up looking like this as a product. So here we have the original base. Its lone pair of electrons is now forming this covalent bond to the incoming proton. Because that proton has come in without its own electron, the product picks up this positive charge. So hopefully that makes it a little bit clearer for you. All right, let's take that a little bit further. So here's our general acid once again, and here's our general base. So as we said on the previous slide, when the acid loses its proton, it becomes A with a lone pair of electrons and a negative charge. And now, because it has a lone pair of electrons, that lone pair of electrons can actually accept an acid. So our acid has actually turned into a base. Acid has become a base. And we refer to this base product as the conjugate base of the original acid. Okay, the acid has turned into a base. Let's look at the actual base as a reactant. So the base starts with a lone pair of electrons. It picks up a proton to form this product. So we've got the base, its lone pair of electrons is forming a covalent bond to that incoming proton. and it picks up a positive charge. But what's important to note now is that what was originally a base now has a proton that it can donate. So our original base has become an acid. When we have this acid forming as a product, we call it a conjugate acid of the original base. Okay, so the product formed by loss of a proton from an acid is called its conjugate base. So there's the conjugate base of the original acid. And the product formed by gain of a proton by a base is called its conjugate acid. So there's the conjugate acid once again of the original base. Isn't that confusing? Is that confusing? I think I've lost everyone. All right, still there? Okay, still there. Someone's must be drinking a lot of wine. All right, you're still there? Good, yes. Drinking wine, hopefully not the wine that tastes like acetic acid. Oh, and beer. All right, there you go, and beer. I'll stick to my coffee and have my wine afterwards. Okay, so that's the concept of conjugate bases and conjugate acids. Yes, always wonderful to read a textbook. You get a lot more information around each of the concepts. So definitely, if you feel like you need more information, definitely do some further reading. Okay, so still on the same concept of conjugate acids and bases, but now we're looking at an actual acid-base reaction. All right, so here's our acid, HBr. Here's water, which is acting as the base in this particular instance. And if we look just at the acid, HBr, when it donates its proton, that acid turns into the bromide anion. So the bromide anion as a product is considered the conjugate base of this acid. So basically it's just the product of this reaction, one of the products of the reaction. All right, water acts as the base in this particular example, so it picks up the proton that was given off by the acid, and in gaining that proton to form the hydronium ion, and this particular product is called the conjugate acid of the original base. Okay, so it's just terminology really. So HBr and Br negative are considered to be a conjugate acid-base pair, and water and hydronium are considered to be a conjugate acid-base pair. All right, so a little bit of terminology. All right, let's now just recap so you understand how the charges actually work. And these are just some simple rules for you. So when any species gains a proton, it will gain a +1 charge. Simple as that. So here's an example: water, no charge, neutral molecule. If it picks up a proton, which it can to form hydronium, it will also pick up a +1 charge, which you can see there. When a species loses a proton, it effectively gains a -1 charge. So here's our example, HBr. It's neutral at the moment, but when it loses a proton, it will pick up a -1 charge. Okay, so just some simple rules there. All right, now you might have picked up already that some compounds contain both an acidic hydrogen atom, that is a hydrogen where the proton component of that hydrogen can be lost, And the same compound also contains a lone pair of electrons. And that means that that compound can act as an acid or a base. And we call these compounds amphoteric compounds. And I'll remember that one student said, oh, I can remember that. I'll just remember the word amphibian. And I thought that's actually quite a good idea. Remember amphibian and you remember what amphoteric means. Not a bad idea. All right, so classic example, water. A water molecule can act as a base. Water can also act as an acid because it satisfies both of those criteria. It contains a hydrogen that can be lost and it contains a lone pair of electrons that can accept a proton. So when water acts as a base, it can accept a proton to form H3O plus, that is the hydronium ion. Water, of course, can lose a proton. So if we remove a proton, then we end up with OH, that is the hydroxide anion. All right, let's move on now to the concept of acid and base strength. What is it that makes an acid or a base strong or weak? How does that all work? And it's really quite straightforward. So first, let's look at what happens when an acid dissolves in water. When it dissolves in water, a proton is transferred. That is, a proton is lost from the acid. And that proton transfer that occurs is called dissociation. When a strong acid dissolves in water, 100% of the acid molecule will dissociate. So 100% of the acid molecules will lose their protons. And that's why it's referred to as a strong acid. And here's an example. So hydrogen chloride is a strong acid, is classified as a strong acid. So that when it's dissolved in water, all of the HCl will dissociate. That is, all of the HCl will give up its acidic proton. To form these products, the hydronium ion, and of course the hydronium ion is coming from the base water. Well, sorry, water is acting as a base in this particular example, and the chloride as a product is what remains from our original acid. All right, note this single reaction arrow is used to denote that this reaction goes to completion. That is, equilibrium lies to the right. And in other words, the forward reaction is favoured. And here are some examples of common strong acids. All right, what about weak acids? When a weak acid dissolves in water, only a small fraction of the acid dissociates into ions, and that's why it's referred to as a weak acid. Obviously doesn't work very well as an acid. And here's a very good example. And in this case, we have someone's favourite, the winemaker's favourite, not really, acetic acid, CH3COOH. Dissolved in water to form the hydronium ion. So remember, this is the acidic proton, the one that will be given up to the base, which is water. So water will then form the hydronium ion, and the acetic acid molecules, which do lose their protons, will then form this product, which is called acetate. All right, but let's look at the reaction arrows. They're unequal reaction arrows. And what are they showing us? So only a very small forward reaction arrow, but a very large reverse reaction arrow. So can anyone tell me what this large reverse arrow actually means? What does that mean? The large reverse arrow, reaction arrow. What does that actually mean? in this particular case? Okay, we have an answer. There are more reactants than products. Yes, yes, you can say that. Absolutely, absolutely. So another way of looking at it, when we have this large reverse arrow, we can say that most of these molecules actually don't react to form these products. That's another way of saying it. But yeah, you're absolutely right. And this short forward arrow is basically indicating that only some of these reactants are actually reacting to form these products. Okay, and here are some examples of common weak acids. All right, and that's illustrated here. So we've got a strong acid, HCl, completely dissociates in water to form hydronium ions and chloride ions. Here we go with a weak acid, such as acetic acid here. And this, a solution of acetic acid would contain mostly undissociated molecules of acetic acid and very few hydronium and acetate ions. All right, now the same thing applies to bases. So when a strong base dissolves in water, 100% of the base will dissociate into ions. Here's our very common strong base, sodium hydroxide, dissolved in water, will dissociate completely to form sodium ions and hydroxide ions. So our common strong bases are sodium hydroxide and potassium hydroxide. When a weak base dissolves in water, and here's an example of a weak base. This is ammonia. And ammonia is another good example of an amphoteric compound. So ammonia can act as a base, it can act as an acid. So when a weak base dissolves in water, only a small fraction of the base dissociates into ions. So only a small number of these reactants will actually react to form the products, which we have here is the ammonium ion and the hydroxide ion. And we can see that that's the case because of these reaction arrows. All right, and that's illustrated for you here. Strong base sodium hydroxide completely dissociates into sodium ions and hydroxide ions. But a weak base, such as ammonia, will contain mostly undissociated base. Very few products. All right, so a strong acid will readily donate a proton, and it forms a weak conjugate base. So here's our strong acid, hydrochloric acid. And because hydrochloric acid very readily donates a proton, that means that the product, which is the chloride ion, has very little ability to accept a proton once again. So it's referred to as a weak conjugate base. The same thing applies to a strong base. A strong base will very readily accept a proton, which means that its product, in this case water, has very little ability to get rid of that proton once again. So this tells us to a certain extent which product is actually favoured at equilibrium. All right, that brings us to the concept of equilibrium and acid dissociation constants. So for a reaction where an acid dissolves in water, and we can see a general reaction there, an equilibrium constant can be written. Okay, where the equilibrium constant K equals the concentration of the products of the reaction. So here's the products here, concentration of the products divided by the concentration of the reactants. Now you don't need to know these formulas at all. All you need to take from this is, just get my pen, all you need to take from this is that where you see these square brackets, as you can see in this equation here, those square brackets in chemistry means the concentration of whatever is written within those brackets. So these square brackets here, for example, means the concentration of hydronium ions or the concentration of water. Okay. All right, so that's the main take home from here. Oh, sorry, let me clear that. All right, so we can rearrange that equation to form a new constant. And this new constant, Ka, is called the acid dissociation constant. Remember, you don't need to know these equations at all, but all you need to know is that the values given for Ka represent the strength of a particular acid. So the stronger the acid, the larger the value of Ka will be. Equilibrium, on the other hand, always favours the formation of the weaker product. And we sort of explained to a certain extent why that's the case on the previous slide or 2 slides ago. All right, so the acid dissociation constant Ka tells us how strong or weak a particular acid is. And here we have an example. So this table from the textbook shows the Ka values or acid dissociation values for common weak acids. And you can see, you'll be familiar with some of these. So of course, acetic acid, carbonic acid, the ammonium ion, you'll be familiar with those. But the important take home from this is that the stronger or the strongest acid from this table, which is the hydrogen sulfate ion, look at the Ka value. So this is a much larger number, for example, than this one down here, which means that hydrogen sulfate ion is a stronger acid than the hydrogen phosphate ion. Okay, so make sure that you can recognise, given a set of numbers, which one is higher than the others. All right, and that brings us to the dissociation of water. So we haven't really talked about pH yet, have we? The pH scale, but this is where we really dissect what the pH scale means. So you know that water is an amphoteric compound. That is, it can behave as both an acid and a base. So that means that 2 water molecules can actually react together in an acid-base reaction. Here we have a water molecule that will act as the acid and a water molecule that will act as a base. And when they do react with each other, which is not very often, and you can tell that from these unequal reaction arrows, the products that are formed are the hydroxide anion and the hydronium ion. Okay, this doesn't happen very often. So in any sample of water, there would be only a tiny fraction of water molecules that will react in that way. All right, but from the reaction of 2 water molecules, another constant can be written where the equilibrium constant K equals the concentration of our products divided by the concentration of our reactants, that is our water molecules. And of course, you don't need to remember that, but what you do need to be familiar with is the actual concept of the ion product constant for water. And here's the abbreviation for that, Kw. So the ion product constant for water, Kw, equals the concentration of hydronium ions multiplied by the concentration of hydroxide ions. So the value is the important thing here for Kw. And here it is. So experimentally, it's been shown that the concentration of hydronium ions and the concentration of hydroxide ions in a sample of pure water, the concentrations are the same. They are equal. And the concentration that was shown for both is this value here, 1 by 10 to the minus 7 molar. So once again, in a sample of pure water, the concentration of hydronium ions is 1 by 10 to the minus 7, so a very small number. And the concentration of hydroxide ions is also 1 by 10 to the minus 7. And here's our first peak at the pH scale. What does this tell you, this number here, when it comes to the pH scale? What is that telling you? Oh. Neutral. Great. That's the one. There it is there. Neutral pH, pH 7. And that number on the pH scale comes from here. Because imagine having a pH scale that had numbers like this written on it. Not very convenient. So what they did was they took this number here and they set that at neutral pH, because if you took a sample of water and you measured the pH, it would come out at pH 7. All right, so that's what pH 7 actually means. It means that the concentration of hydronium ions and hydroxide ions are equal. If we multiply those numbers together, that is the concentration of hydronium, concentration of hydroxide, multiply them together, you will get your ion product constant, that is Kw. And this is the value 1 by 10 to the minus 14. This is your Kw value for all aqueous solutions. Let me clear that. All right, so given that we've got that constant, that 1 by 10 to the minus 14, Kw, if we know the value for this or this, then we can calculate the value for the unknown. Very simple. So to work out the concentration of hydroxide ions in any solution, we would simply take the Kw value, that is 1 by 10 to the minus 14, and divide that by our known value for hydronium ion, concentration of hydronium ion. Same thing applies if we're trying to work out the concentration of the hydronium ion. We would simply say Kw divided by our given value for the hydroxide. That is, of course, Kw is 1 by 10 to the minus 14. Divide that by the given value for that. And let's look at an example. So one or two of your tutorial questions will relate to this slide. And here's an example for you. So if the concentration of hydronium ions in a cup of coffee is 1 by 10 to the minus 5 molar, then the concentration of the hydroxide ions can be calculated very simply as follows. So this is our unknown, here it is, equals Kw divided by our value for hydronium ions. What is Kw? Here it is, 1 by 10 to the minus 14. We divide that by the value that we were given for hydronium, which is 1 by 10 to the minus 5. And then if you plug that into your calculator properly, into your scientific calculator properly, you should get this answer here. So this is a very good one to practice. Make sure that you can do this using your scientific calculator. and make sure that you come up with the right answer. If you don't and you can't work it out, by all means, let me know and I can give you a tutorial on that. All right, so in this cup of coffee, we've worked out that the concentration of hydronium ions is actually greater than the concentration of hydroxide ions, and therefore the solution is acidic overall. So how do you know that? That it's acidic just based on that? Well, here we have a table, a great table that sums all that sums that up for us. All right, so let's look at that. So we've already said that when the pH is neutral, that is, it's pH 7, that means that the concentration of this species is equal to the concentration of that one. That is, the concentration of hydronium is 1 by 10 to the minus 7 molar, or simply just 10 to the minus 7. And of course, there's our pH 7 right there. And that is equal to the concentration of hydroxide ions. All right, in an acidic solution, the hydronium ion concentration will be greater than this one here. That is, the hydronium ion concentration will be greater than 10 to the minus 7, and the hydronium ion the hydroxide ion concentration will be less than 10 to the minus 7. In a basic solution, it's the other way round. The hydronium concentration will be less than the hydroxide concentration. That is, the hydronium will be less than 10 to the minus 7, and the hydroxide will be greater than 10 to the minus 7. So keep this table in mind. One of your tutorial multiple choice questions will present you with responses which you don't actually have to work out. All you need to do is refer to this table, and this will help you very quickly figure out the correct answer to one of those questions. All right, so let me just look ahead a little bit. All right. Okay, so at this point, what is pH? What is pH? We already have a clue that pH, the values on the pH scale, are really a more convenient method of representing pH. Yep, they're just a more convenient method of representing pH. So once again, we've got 0, we've got 7 for neutral, and we've got 14 up here. So the numbers that you see on the pH scale simply represents the negative log of the concentration of hydronium ions. But as I said earlier, if we just used those actual concentrations of hydronium ions on the pH scale, it wouldn't be very convenient using numbers like this. So they've basically just taken the negative logs of these numbers. In other words, for this number, 7 is this number here. Yep. If you had a number like this, 1 by 10 to the negative 5, what pH would that be? What would be the negative log of that number? Simple, 5. And that would represent pH of 5. Okay, so very easy. When you're confronted with a number like this, where this number here is exactly 1, then you know that this number here is exactly what the pH is. It's when this number here is not exactly equal to 1. So if, for example, it was 1.2 by 10 to the minus 5, okay, then you know that the pH is roughly 5, but you don't know exactly until you actually start using your calculator. Okay. All right, so, and we'll come back to the pH scale in just a minute. So let me clear all that. All right, so pH is simply the negative log of the concentration of hydronium ions. So the lower the pH, the higher the concentration of hydronium ions. And we've seen that in an acidic solution, that is where the pH is less than 7, the hydronium ion concentration will be greater than this number. In a neutral solution, that is pH 7, hydronium will be exactly this number. And in a basic solution, that is where the pH is greater than 7, the hydronium concentration will be less than 1 by 10 to the minus 7. All right, so a couple of extra calculations here. And these, of course, you really do need to use your calculator, your scientific calculator. All right, so let's look at how we calculate pH given a value for the concentration of hydronium ions. And here's our question. If the concentration of hydronium ions equals this value here, then what would be the pH? So remember, and this is a really good check, when you're given a question like that, you know that the pH value, the answer will be close to 5. You know it won't be exactly 5 because this number here is not exactly 1. Okay, so how do you do this using your calculator? You simply punch into your calculator negative log, open bracket, 1.2 by 10 to the minus 5, close bracket. And then if you've entered that correctly in your calculator, you should get this answer 4.92. How do you know you're on the right track? Compare your answer to what you see here. It's pretty close, so you know you're doing it right. Just a tip for you, when you enter this negative in your calculator, don't use the subtract button, the subtraction button. Don't use that button there. Look for a button that has the negative in brackets, okay? All right, and don't forget these brackets here, all right, to enclose this value. All right, 4.92, and as you know, the solution is acidic because the pH is less than 7. All right, so practice this and make sure that you can do this on the calculator and get the right answer. All right, what about the reverse? What if you're given a value for pH, but you need to calculate the hydronium ion concentration? So this is the reverse of what we've just done. So that means that we have to use the anti-log rather than the negative log. So let's look at how to do that. So we're given a pH of a solution at 8.5 and we have to work out the hydronium ion concentration. A very simple alternative method that students really like because it's so simple is simply to put this into the calculator. So this is a very easy way of finding the anti-log. Punch into the calculator 1 multiplied by 10 raised to the power of negative and whatever the pH value is, which in this case it's 8.5. There it is there. So that's all you need to put into the calculator to find the anti-log of this number here. And if you do that correctly, you should get this answer. 3 by 10 to the minus 9, well, you won't get molar, but that's the correct unit to use. Well, you'll either get 3 or 3.2, depending on the calculator that you're using. But if you do get that answer, then you know you're on the right track. Another way of checking, of course, is to look at what this number is here. You've got a little 9 here. That's pretty close to 8.5. So you know you're on the right track there. And of course, this is a basic solution because the hydronium ion concentration is lower than 1 by 10 to the minus 7. All right, so Now let's have a look at something here. No, we don't want that. Oh, I haven't opened it. Hold on, let me just bring something up. Documents. All right, just bear with me. Lectures, PDFs. Here we go. pH scales. There we go. Can everyone see the pH scale on? All right, someone has. All right. Oh, very good. You've tried to work it out. All right, let me go back. Okay, so you've got 1, 2, 3, 4, 5, 6, 7, 8. That's perfect. That's exactly what I have here. So spot on. All right, pH scales. All right, so let's have a look at some examples of pH scales. So this is a nice basic pH scale everyone's familiar with. Yeah, you did. It didn't come up with this with the value in scientific notation, but it's exactly the same number. So well done. Good. All right, so basic pH scale, everyone's familiar with these values, 1 to 14, 7 being neutral, and then below 7 acidic, and above 7 basic. All right, so that's not too bad. Here's another example, still the same sort of thing, showing these normal values, but here we can actually see what pH actually means. Obviously expresses the acidity or basicity of a solution, and it means power of hydrogen. So that's from a different textbook. If you've got Biology by Campbell, published by Pearson, that's also an excellent textbook. All right, now here's a better one. Let me make that a little bit smaller. A little bit smaller. Go 50%. Okay, so this one is much better because it shows not only the normal values that you expect on the pH scale, but it also shows the concentration here of the hydronium ions and the concentration up here of the hydroxide ions. And what's really nice is that if we just start by looking at neutral pH, 10 to the minus 7 is our concentration of hydronium ions, and this area here represents that concentration, and that area is the same as this given area for the hydroxide ion. All right, as we start to move into the acidic portion of the pH scale, you can see this area for hydronium gets larger. Now it's at 10 to the minus 6, while this area for hydroxide gets smaller. So I think this is a really nice representation. As we become even more acidic, we've got less hydroxide. But if we look down here, as we become more acidic, we have more hydronium. And the same thing applies if we go into the basic part of the pH scale. We can see that the hydronium ion concentration gets less and less, but the hydroxide concentration gets greater. So I think this is a really nice, very nice representation of the pH scale. All right, so let's go back to our lecture now. All right, so we've done that. All right, so there's different types of acid-base reactions, but here we have one of the most common. And this type of acid-base reaction is called a neutralization reaction. And it's a type of acid-base reaction that produces a salt and water as the products. So you can appreciate how important it is when we mention salt as a product. All right, acid plus a base, in this case a metal base, nth metal, will react to form water and our metal salt, Ma. So of course the acid HA has donated a proton to the hydroxide portion of this base to form water. The remaining part of the acid A binds to this metal here, to this metal portion of the base to form our salt. So let's look at an actual neutralization reaction on the next slide. Here it is. Here's a classic neutralization reaction. Hydrochloric acid HCl plus sodium hydroxide. This is an example of a metal base. In this reaction, which goes to completion, as you can see by this reaction arrow, the products will be water and the metal salt, sodium chloride. All right, we can actually take out individual ions, which we can see here. So if we firstly write this reaction out as individual ions, so for example, the proton and the chloride, which comes from the HCl, and the sodium ions and the hydroxide ions, which together form the base, sodium hydroxide. Now let's look at the products. So of course we've got water, and then we've got the sodium and chloride ions from sodium chloride. Okay, so once we write this out as individual ions, we can actually take out ions that appear on both sides of the equation but are unchanged. And those ions are chloride and sodium. So we'll cross them out, chloride and sodium, cross them out there, and that leaves us actually with the ions that are the most important in this particular reaction. That is the protons and the hydroxide, and of course the product that is formed, that is water. And then if we write them out separately, what remains is called the net ionic equation. So the ions that we actually crossed out are called spectator ions. And what we have remaining here after removing the spectator ions is the net ionic equation. That is, protons plus hydroxide will react to form a molecule of water. All right, finally, very, very briefly on buffers. Very briefly on buffers. So you're probably aware that a buffer is a solution whose pH changes very little when you add a small amount of acid or base. It resists changes in pH. So you basically have to keep adding more and more acid and base, and then finally that buffering capacity will be broken and the pH will have to change. But initially that solution will resist changes to pH. Very, very useful. All right, so let's consider what would happen if you just had a normal solution, and you add a little bit of HCl, a little bit of acid. What will happen immediately if you were measuring the pH of that solution? Immediately the pH would start to decrease. Okay, and that happens instantly. And of course, if you added some base, small amount of strong base like sodium hydroxide, you were measuring the pH of that solution at the same time, immediately you would see an increase in the pH. But that doesn't happen when you are using a buffered solution. A buffered solution, if you add a small amount of HCl, the pH will only decrease very slightly, And as I said, you would have to keep adding the acid and keep adding it, and then eventually it will start to really drop. And the same thing applies with adding bases. All right, so what are buffers? Buffers are solutions composed of roughly equal amounts of an acid, a weak acid, and its conjugate base. Roughly equal amounts of an acid and a base. And the buffer resists changes in pH because any added base, for example, hydroxide, will react with the weak acid. Any added acid will react with the base. So therefore, you'll have your amounts of acid and base in that solution will change slightly, but overall the pH won't change a great deal. So that's basically where the buffering capacity comes from having both an acid and a base in the same solution. Oh, just clear that. All right, so if we take this example, once again, we've got acetic acid, a weak acid, and remember it's classified as a weak acid because very few of the acetic acid molecules will actually give up the acidic proton. And we've got water here, and here are the products, hydronium ion and acetate. So remember, in a buffered solution, we will have equal amounts of this base, this conjugate base, which is acetate, and equal amounts of this weak acid. So if we add a little bit of acid to this buffered solution, what will happen is that the proton that's donated from this acid will be picked up by the base. So that means we'll have a little bit less of the base and a little bit more of this acid. But as I said, overall the pH doesn't actually change very much. Okay, the same thing happens if we add a little bit of base to this buffer equilibrium. If we add a little bit of base, then basically we alter the amounts of our weak acid and our conjugate base, but overall the pH doesn't change a great deal. And in this case, the reaction is driven to the right. All right, so that's very briefly on buffers. And that is it for tonight's lecture. So I wanted to actually start on the last of our chemistry lectures, which is solutions. But I think that this lecture is enough for one night. So we could always pick up the solutions lecture next week. All right, so let's see what we've got in terms of tutorial questions. So these are based on our acids and bases lecture from tonight. This set of questions is assessed and worth 4%. Okay, and these are due on Monday. But I had a thought when I was looking at this, that given that you have something else coming up, very important coming up this coming weekend. Does anyone know what assessment's coming up this weekend for living systems? Online test, great. Mid-semester, yes. No, not end of semester, mid-semester. Mid-semester test is coming up. Yep, absolutely. That is coming up this weekend. So I think it's probably a bit mean having the two questions due at roughly the same time as the mid-semester test is due. So what I'm going to do, I'm going to extend the due date for these questions. I'll extend them by, extend the due date by an additional week. So you don't have to stress trying to get through these questions, prepare for the test at the same time, as well as probably other assessments that you've got going on for other subjects. So let's have a look at the subject learning guide for your assessments. Okay, so where are we? Yeah. All right. So here we are in week 7. So the online mid-semester test is available from this Friday. It'll open at 6 a.m. and then it will be open until Monday, and it will close at 11 p.m. So remember, you can start the test at any time during this period, but once you start, you will have to complete it. You'll have to complete it. You can't come back to it. All right, so how long does it go for? So the test will be, you'll have 2 hours to complete the test. So once you start it, you'll have 2 hours to complete it, which means don't start the test on the Monday evening at 10 p.m. because then you're only giving yourself 1 hour to complete it, because the test will actually shut down at 11 p.m. So once you, good question. So which topics will the mid-semester test cover? The mid-semester test will only cover weeks 1 to 5. Only weeks 1 to 5. That is lectures 1 to 6. So make sure you only focus on those 6 lectures, and in particular focus on the tutorial questions that were associated with lectures 1 to 6. Another question, closed book? No, it's open book. Open book, so you're doing it from home, so you can have your notes with you, but remember, you won't have time to constantly be referring to your notes. You won't have time to be doing Google searches for the answers. You will run out of time. So, even though, yes, you can have your notes with you, by all means, it's probably better that you just have maybe a summary page with you. Have a bit of a summary page with you, just a few notes that you can very quickly refer to, because you will run out of time. If you're not prepared and you're not treating it as you would a closed book test, then you will run out of time. So it's an important assessment. It's worth 25% of your marks. So it's well worth preparing for. And all right, another question, multi-choice. Yes, there is multi-choice. There's multi-choice. There's true and false. There are some short answer questions, and there are some calculations. So when you actually click on, I don't know if you actually can. Let me see if I can do something here. Let me see. Oh, no, I can't. That's all right. So when you actually click on the mid-semester test in Moodle, when you click on it, it'll actually show you how many multiple choice questions, how many true or false, the weighting assigned to each. So those ones are obviously worth 1 mark each. And then it'll show you the number of short answer questions and calculations. Now, you don't have to do it in order. You can actually you can flag questions. So you hit the flag question, which means you can skip that question or those questions, and then you can come back to them later on. Okay. What's the percentage of this test? So this test is worth 25%. Let me just double check. There it is there, 25% for the mid-semester test. Okay. So remember, concentrate on those tutorial questions. They are an excellent guide as to the types of questions that you can expect to get. So I promise you that there will not be any surprises. So really focus on understanding those tutorial questions. And some of them might even come up again in the actual test itself. All right, so that's what's coming up this week for Living Systems. So where are we? Okay, so that's the test. This is the set of tutorial questions, but I'm going to give you an extra week for this one, for this set of questions on acids and bases. So I'll change that on Moodle. Oh, okay, so here we go, prac report number 1. Yeah, no problem. So the question is, what do we do about the prac report for the people that didn't get to attend it in person? All right, good question, and I'm coming to that. All right, so here we have prac report number 1 due for students that managed to attend that last prac that we did on the standard curve. So for those students that attended, it would be really good, very useful for you if you did still submit your prac report on this date, on the 1st of May. But if you don't, that's also fine. Given the situation this semester, I'm not going to insist on that, but instead, all students can submit prac report number 1 on this date, the 15th of May. Okay, so for those students that didn't attend that prac, well, for all students, in fact, I've put up a series of video recordings of that prac demonstration. So get onto Moodle and you'll see under the heading contents, at the bottom, it'll say prac standard curve. Click on there and you'll see a series of short video recordings of the prac demonstration. It shows the results of that prac, and given that information and a little bit more information that I've put on there, you should all have enough information to write up that prac report. So have a look at it. Let me know what you think about those video recordings. I'd really appreciate any feedback because I've been doing, well, we've been doing a lot of video recordings over the last few weeks. So I'd really appreciate some feedback on how those recordings are and what we can do to improve in the recordings. Okay, another question, only 1 prac report instead of 2? No, there are still 2 prac reports. So the second prac report will be written on the prac called acid-base titration. And we've nearly finished. I've got a series of video recordings of the prac demonstration on acid-base titration. Nearly finished. So that report number 2 is due here. Prac report number 2 due on the very last day of semester. Okay, the 29th of May. All right, but those recordings will be available soon. I've got them all up there. You can't see them yet because I just have to do one final video recording, which is just basically to help you through the calculations for that particular prac. Just very, very simple calculations. So that's the prac reports. And of course, we need to just talk about the final exam. So the final exam, so all final exams, we're planning to put them all online. They'll all be delivered online. The reason I haven't quite announced that yet is because I'm still waiting on approval. So I've got approval from La Trobe University for all those assessment changes. That is to put all the final exams online as open book online exams. But I still need to get approval for our international students, and that comes separately to La Trobe. There's a whole different process that I have to go through. So I've submitted all the paperwork for that. I need to have all the approvals. All the approvals are due Tuesday next week. So hopefully by then, or after Tuesday next week, I can actually confirm that final exams for all students will be available online as open book online exams. So that will be not just for living systems, but for all your subjects that have final written exams. Okay, so that's it there, final exam. Now also, I'll let you know, but you can see here that if it was a written exam, it would be the duration of the written exam would be 1.5 hours. Now, this will be a bit different with the exam going online, because doing an exam online is always much slower than doing a face-to-face written exam. So the duration will actually increase for the online exams. Where the duration becomes too great, then the recommendation from the La Trobe Community of Practice, which deals with online exams, is that that one long exam should be split into two shorter exams. So that's what we're planning to do. All right, question. So does Ag Systems and Technology have a final exam? No, it does not. But all students that are doing Ag Systems and Technology, your final marks will be withheld. You'll be placed on a withheld at the end of semester because, of course, we can't deliver the tractor operations course and the chemical users course yet. All right, another question. So no assessment is deferred. Yes, there are some assessments that are deferred, like Ag Systems and Technology. There are 3 other subjects where students will be placed on withheld grades at the end of semester. 2 of them are equine subjects. And the 4th subject is, let me think, Wine Chemistry 1. So any students that are doing Wine Chemistry 1, which I don't think will be any students in this subject because it's a second year subject, they can't actually do their wine analysis training in the lab, which they really need to do in order to be able to do the practical exam. They have a practical exam for that subject. So that assessment is deferred. And therefore those students, their final grades will be just withhelds until such a time as we can run the prac training so they can do the prac exam. So any other questions on any of your subjects? All right, just to double check, you said the mid-semester exam is on content up until tutorial 5. Yes, I believe that's correct. Let me have a look. Let me have a look. So we've got 6 lectures. I think we covered the 6 lectures in 5 weeks, so that would be right. But let me just double check. So everything we've done so far apart from tonight. No, not everything that we've done so far apart from tonight. Let me just check for you. I believe it's everything that we did up to and including biological macromolecules. Where are we? Okay, so weeks 1 to 5. In weeks 1 to 5, we covered, yes, up until and including lecture 6, which was biological molecules, yes. So lectures, lecture 1, matter and measurement, lecture 2, atoms and the periodic table, lecture 3, ionic compounds, lecture 4, covalent compounds, lecture 5, chemical reactions, and lecture 6, biological molecules. So that is tutorials. I'm just checking. Tutorials. Tutorials 1 to 4. Tutorials 1 to 4 cover all of those 6 lectures that I just mentioned. Tutorials 1 to 4. Okay. All right, so that's all you really need to study. I mean, that's enough to study, but that's all you should be focusing on for that test. Okay, any other questions? All right. Oh, I know there was some confusion in one of your other subjects regarding word count. Is everyone now clear on word counts for assessments in other subjects? In particular, there was some confusion in Agronomy 1. Has that all been sorted? Oh. Okay, sounds like it has. Confused about the titles. Oh, about whether to include titles in word counts. Yeah, yeah. Look, I don't blame you. There's been a lot of confusion over the past probably 6 months regarding word counts, and that's because traditionally we had one method of assessing word counts, and then last year with increased sort of compliance and oversight by La Trobe University, the rules actually changed. So there's probably still some residual confusion around word counts. So really important that you actually look at something like this. Let me bring this up. The guidelines that you're given for each assessment. Let me just bring one up for you. I'll just bring up one of the living systems ones. Where are we? Subject outlines. No, it's not it. That's not it. Here we go. Calibration. Guidelines, marking rubrics. I'll just bring this one up, share. All right, can everyone see that? Can everyone see this document for lab reports? Yep. So this document, you'll find this on Moodle. This is guidelines, one of the guidelines documents for lab reports in living systems. And what you will see is, not exactly what I thought you would see. Apart from the marking rubric. So the marking rubric is obviously important because it tells you how many marks are allocated to each part of the report. Okay, let me find the document that I was actually after. Here we go, guidelines. This is the one. All right, so you'll also find one. Okay, you'll find this document here on Moodle under assessments, and you will see, here we go, word limits. So look for this, something like this, in your assessment guidelines. Okay. So it's all written here for you. Word count. So the word count will be calculated using all the text, including headings, including in-text citations. So basically everything in the report, but not the reference list and not the text in any of your figure or table captions. Okay, so everything else is included in the word count, which is a little bit different to how it used to be. And I think that's where the confusion lies. All right, so make sure before you start on your report or reports, make sure that you look at these guidelines, and definitely let me know if you have any questions. Okay, so the PRAC report has every PRAC included in it. No. So one PRAC report will be written on the standard curve PRAC, and the second report will be written on the acid-base titration PRAC. Okay, so 2 reports, 2 practicals. And you can refer to those practicals in your PRAC manual. So the PRAC manual is also on Moodle. Okay, so have a look at those 2 PRACs for your PRAC reports. Okay, now I think I missed a question. Let me have a look at that. Okay, no, all good. Yeah, so when you have a looking at that PRAC manual, focus your attention on those 2 practicals. Standard curve PRAC, so that one's called determination of concentration using a standard curve. And the other PRAC is the acid-base titration PRAC. Okay, so that's what you're writing your 2 reports on. And don't forget also there's an example of a PRAC report on Moodle as well in the additional information folder. So have a look at that. It's pretty good. It's not perfect, but it's quite a good example of a PRAC report. So also have a look at that before you start writing your own. Okay, any other questions for me? Okay. I should stop the recording, shouldn't I? Just in case anyone wants to chat. All right, stop recording now. Stop recording.